All right, so we just looked at a constant function and a linear function, and the next thing I want to look at is power functions. Now, in the last section, we actually used the definition of the derivative to show that the derivative of x squared was equal to 2x. Okay, so that's a power function. So we know that the derivative of x squared is 2x from the last section. And now we're going to look at x cubed. All right, so this is just another power function. I'm just putting a different power on it, right? So we're going to use the definition of the derivative. So the first thing I want to do is just find f of x plus h. All right, because there's a lot of algebra involved in writing it and then simplifying it out. So essentially, we're just going to replace x with x plus h. So f of x plus h is just going to be the quantity x plus h cubed. All right, but I'm going to expand that out, which takes a little bit of work, right? This x plus h cubed just means x plus h times quantity x plus h, 3 times. So what I'm going to do is I'm going to take 2 of those factors and square them. So if I take x plus h times x plus h and FOIL it out, I'm going to get x squared plus 2hx plus h squared. Okay. Now I just need to use the distributive property and distribute the x plus h across all the terms in the second factor. Okay. So first of all, I'm just going to multiply everything by x. So I'm going to get x cubed plus 2hx squared plus h squared x. All right, all I've done is take the x times everything in the second factor, and then I'm going to multiply everything by h. So I get plus hx squared plus 2h squared x, and then plus h cubed. All right, so I've expanded it all out, and now I need to combine like terms. So I have a term with an x squared here and an x squared here. So I have 2hx squared and 1hx squared, which I can combine into 3hx squared. So we have 3hx squared. And then I have a h squared x and a 2h squared x. All right, so I can combine those into 3h squared x and then plus h squared, or h cubed, sorry. All right, so now I've got f of x plus h, right? I didn't want to have to do all that algebra and carry along the fraction and everything. So now we're going to look at the f prime of x. So f prime of x is equal to the limit as h approaches 0, right? And I'm going to take f of x plus h, which is x cubed plus 3hx squared plus 3h squared x plus h cubed. All right, and I'm going to subtract f of x, which is just x cubed. And I'm going to divide all of that by h. All right, now, so the x cubes will cancel, and you can see that everything that's left in the numerator has an h in it. And so I would like to be able to cancel that h. So let's go ahead and pull an h out. Or you could think of just dividing each term by h, but let's just go ahead and pull a factor of h out. And what I have left is 3x squared, and then plus 3hx plus h squared, right? I just pull the factor of h out of each term that's left in the numerator, and I'm going to divide all of that by h. Now you can see we can cancel common factors. We can cancel an h. And now what we're doing, we take the limit as h approaches, oh my, why do I keep writing? H approaches 0, not infinity. H approaches 0, right? The factors that are these terms here that have h in them, as h goes to 0, those will just get smaller and smaller and smaller and smaller. And the only thing I'm going to have left is this 3x squared term, right? That doesn't even have an h in it. So it's not going to change as h varies. So what I have left is just 3x squared, and the rest of these terms essentially go away because I'm allowing h to go to 0. I'm letting it get smaller and smaller, and so they're going to just get so small we can't even see them anymore. So the derivative of x cubed d dx of x cubed then is 3x squared. Okay, so let's compare that to what we got with x squared, right? Notice we got 2x. So essentially the 2, right? The 2 seems like it comes down out front, and then we reduce the power by 1. So this is the same thing as 2x to the first power, right? I just don't need to write the first power because anything to the first power is just itself, right? Here you can see where the 3 looks like it kind of came out front, and then we reduced the power by 1, right? Now, I'm not going to go through the proof of this, of the power rule. There are probably proofs you could go out and see online. In general, I think typically it's you use the binomial theorem to, because you have to expand x to the n, right? We would like to know the derivative of a general power function, which would be x to the nth power, right? But if you want to use the definition of a derivative, you'd have to expand x plus h to the nth power, and you need the binomial theorem to do that. So I'm not going to get into that, but we're going to use we're going to stand on the shoulders of giants, of better mathematicians, and who have come up with a formula for the power rule. All right, so if you have a power function, you have x to the nth power, the derivative of that power function is n times x to the n minus 1th power. Okay, so we just kind of bring the power down to the front and then subtract 1 from the power. And that's the power rule. And that's what we're gonna practice using that next. Okay, so this is just a summary of the 3 things we just looked at. We looked at the constant function, a linear function, and then a general power function. And now in the next example, we're going to look at applying the power rule and what these general rules that we've learned.